So induction hypothesis. So what induction hypothesis I should make here? Assume that so induction hypothesis means I am assuming that this statement is true. So assume that statement is true for, and then from that I am going to prove for k plus 1 sets, right? So assume that if a1, a2, ak are any sets, so any sets means our sets, what these sets are, that is not important. How many sets are, that is important for us, because a1 contains fruits, a2 may contains cities, a3 may contains any planets, whatever. What are the members of set, that is not important for us. What is important, how many sets? So k sets. Then a1 union a2 union ak, its complement is same as a1 complement intersection a2 complement intersection ak complement. So this we are assuming now, right? So this is assumption or induction hypothesis, and therefore what is a next third step? So step 3, inductive step. So inductive step. So in inductive step, what we want to prove? In inductive step, we want
k plus 1
to
for
prove for k plus 1. N is equal to k plus 1. Right? That is what we want to prove that if a1, a2, ak plus 1 are any sets, then so this is we want. We have not started its proof. So then so a1 union up to ak and ak plus 1. So this complement of this whole union, we want to prove that it is to be a1 complement intersection a2 complement and so on intersection ak plus 1 complement. So it is not necessary that key sets which we assume in induction hypothesis in second step are same a1 a2 ak, right? Not necessary. The induction hypothesis says that the statement holds for k sets, doesn't matter what are your sets. Similarly, now we are choosing k plus 1 sets, so not necessarily the same sets. We are choosing some k plus 1 sets, and these sets might be different sets, right? So this we want. Now consider. So consider union a1 union. Uh, Now consider union of these k plus 1 sets. So a1 union a2 union ak union ak plus 1 and its complement, that is what I want to calculate now. So uh, if I split this union in two parts, a1 union a2 union a1 union a2 union a3. So if I split union into two parts up to ak, so union up to ak and its union with ak plus 1, the same thing, right? I can split in this way, no harm in splitting the bracket. I will just look at A1 union up to AK first, and then I will look at AK plus 1. So I can just split this. So this union, I can write it as some set B union AK plus 1. So what is set B now? So where B, because B is a set A1 union A2 union AK. So union of this K sets itself is some set. That set I am calling it as B, right? And therefore I can write this union as B union AK plus 1. B is what? Set, which is union of all these K sets, right? And therefore ultimately what I have in this step, I have complement of union of two sets. But already we know that if you have two sets, then complement of union is intersection of their complements. So therefore can I say that this is same as B complement intersection AK plus 1 complement. Can I say this immediately? Right? Because these
Yes.
are only two
Yes,
sets,
sir.
and we are sure about two sets. We have proved. But what is B complement by induction hypothesis? B is union of A1, E2, and AK. And by induction hypothesis, we are assuming that the complement of union of K sets is same as intersection of their complements. And therefore, what is this? A1 union AK, its complement. B is what? Union. Intersection with AK plus 1 its complement, right? Because B is union of A1 A2 AK, and but by induction hypothesis complement of union of K sets is A1 complement intersection A2 complement intersection with A K complement. This is what this bracket, right? This bracket is same as this by induction hypothesis. Now its intersection with A K plus 1 complement. This bracket I have written in this way. It is possible by induction hypothesis, and AK plus 1 complement as it is. So ultimately what we got, A1 union A2 up to AK plus 1 its complement is A1 complement intersection A2 complement and so on up to AK plus 1 complement. So hence thus result is true for n is equal to K plus 1, right? So result holds for n is equal to K plus 1 clearly. Hence by induction, can I say that A1, I have n number of sets A1 union An, its complement is equal to A1 complement intersection A2 complement intersection An complement. So for any natural number n, right? So can I say now here it is true for any number of sets? You take 100 sets or 200 sets, doesn't matter. The result is true, right? So is it clear?
Yes, sir.
Fine. So now similarly you can prove the second statement. What is second statement? If you have n sets A1, A2, uh, An, and their complement of intersection is same as A1 complement union A2 complement so on An complement for any natural number n, right? Suppose now you have n sets. So prove this. This is similar to the previous case. Prove this. This is exercise or homework, you can say. So you try to write down the proof of this. Fine. So that means here, how do we apply induction? Because here n is equal to 2 case was needed to prove, and therefore base case becomes n is equal to 2 in this case. So let me note something here. So if a1, a2, an are sets, then we write union a1 union an. So we want to take union of all these sets, and I can in short I can write it as a k is from 1 to n, right? So this is a short way to write down union of n sets, right? The meaning of this notation is a1 union. So n running from 1 to n, that means first n k is equal k running from 1 to n. That means first I will choose k is equal to 1. So a k a1, then n is k is equal to 2, union with a2, union with a3 up to union with an. That is what the meaning of this notation, right? That you should remember, because we will be using such kind of notations in future. So similarly, a1 intersection a2 intersection an. Suppose I want to express such kind of intersections, then it is same as intersection of a case. And how, which a case? So k is from 1 to n. So a1 intersection a2 intersection and so on. And therefore using this notation, thus De Morgan's law becomes in general, version of the, what will be the general version of De Morgan's law? Key ak k is from 1 to n, right? Union of ak k is from 1 to n. This is a set union of all this. Its complement, that means it is a complement of union. By De Morgan's law, what is it? Intersection of complements of all these AKs. So AK complement and K is from 1 to n, right? So I have each AK and I am taking its complement. So A1 complement intersection with A2 complement intersection with, and so on. And therefore, in short, I can write down De Morgan's law in this way. What is another version of De Morgan's law? Intersection of AK, K is from 1 to n. Its complement is union of all these AKs and their complements, right? So K is from 1 to n. So this is how we write union or intersection of many sets in short, right? So that you can understand. Now let us see one more example of induction. If x is greater than, if x is a real number and it is greater than -1, then, so if x is greater than -1, then 1 plus x raised to n is greater equal 1 plus nx for all natural numbers. So this statement we want to prove in general for every natural number. So if your number, real number is greater than -1, then 1 plus x raised to n is greater equal 1 plus nx. This is our statement. And so our statement Pn is this, right? So we want to prove this for each natural number. This is true. So here, what is Pn? Statement Pn is if x greater than -1, then 1 plus x raised to n is greater equal 1 plus nx for all n greater equal n. This is our statement. So what is the first step? So we shall prove by induction. So because we want to prove this statement for all natural numbers, so we shall prove by induction. Induction on n. Induction on n. We want to prove for all natural numbers. Okay, so in induction, what is the first step? So step 1. What is step 1? Base case. Right. So what is the base case? Prove for. So try to
Yeah.
define n is equal to 1. So try to prove the statement for n is equal to 1 case, and then for n is equal to 1. So for n is equal to 1, what is a 1 plus x raised to n? 1 plus x raised to n is 1 plus x raised to 1, right? And this is actually 1 plus x raised to 1, that means it is 1 plus x, and it is same as, I can say that it is greater equal 1 plus 1 times x, because 1 times x is x, right? And it is 1 plus nx because n is 1 in this case, right? Therefore statement hold for n is equal to 1. No doubt the statement is true for n is equal to 1. Now next step, step 2.
What if the statement is
Uh,
not, what if the statement does not hold for n is equal to 1?
why? What is the statement?
No,
There are
no.
many.
Okay.
There are many statements which do not hold for n is equal to 1. Right?
Okay. Yes.
For example,
So he is
uh,
asking that if the statement does not hold for n is equal to 1, then what to do?
So do
then
we take
we
another number?
see. No. See, logically, if you want to prove that it is true for all natural numbers,
Hmm.
then it must true for n is equal to 1. Otherwise, statement is wrong
Yeah.
and will not try to
Yes.
prove such statement. Right?
Okay. Okay.
Our statement itself is we are asked to prove that it is true for all natural numbers. If it fails for some natural number, then
Hmm.
statement itself is false. So we
Yeah.
cannot prove at all.
Okay. Yeah. Right.
Right?
Yes. Okay.
Very good. So assume that. So second step, induction hypothesis. Assume that the statement hold for n is equal to k. So assume that statement is true for n is equal to k. That is, if n is equal to k, then 1 plus x raised to k is greater equal 1 plus kx, and this is for particular k. We have chosen some k, and what k, that doesn't matter, right? We have chosen some k greater equal 1 or greater than 1. Then you pick up any k, and from that, are you able to prove for next? That is our main issue, right? From you pick up any k, and then uh, for, right, let me say here, for some k greater than or equal to 1. So consider, so what is our step 3? Inductive step. So what we want? what we want to prove, if n is equal to k plus 1, then the statement is true for that n, that means k plus 1, that is 1 plus x raised to k plus 1 is greater equal 1 plus 1 plus k plus 1 times x, right? This is what we want. So k plus 1 times x, this we want, right? This we want, this is not proof. Immediately we cannot say this is true, but with this we want. We want to prove this. Now, so let us start with, so consider, so let n is equal to k plus 1. Assume our we are choosing k plus 1. Then let us check whether result is true. Then start with 1 plus x raised to k plus 1. Let us start with this and see what happens. 1 plus x raised to k into 1 plus x. Certainly I can split this k plus 1 exponent k plus 1, I can split in this way, right? I will split this k plus 1 into two brackets. Is it possible?
Yes, sir.
Yes, sir.
Yeah,
Yes, sir.
so certainly it is possible. Okay, fine. How to use induction hypothesis now at this stage? How to use induction hypothesis?
So we can write 1 plus x to the power k in the equals 1 plus kx.
Right, that is what we have already assumed. So 1 plus x to the power k is, so this bracket is greater equal. So let me first of all, let me not write greater equal, then we'll see what should be the expression. So 1 plus x to the power k and 1 plus kx, which is bigger? So 1 plus x to the power k, right? And 1 plus x as it is. 1 plus x as it is. And therefore now you compare this expression and this expression, which which expression or number in fact is bigger,
The left one.
right? So this number is bigger, and this is because if a is greater than b and c is positive, then ac is greater than bc, right? This is certainly true provided c is positive. If c is not positive, then we are not sure. And why where the c positive makes sense in this case, in our case? Why 1 plus x is positive? So 1 plus x is like c in this inequality. So why 1 plus x is positive?
Because x is greater than negative 1.
Exactly, because this is our assumption. That's why this assumption is very essential. Otherwise, we will not proceed, right? So this assumption is very essential. Otherwise, you will be stuck at this stage, right? We cannot say that it is greater equal. And therefore, logically, when we make some statement and we include some words or some expression, each and every expression, each and every word makes sense. And therefore, x greater than minus 1 makes sense here. Otherwise, we will not be able to prove this. Correct? Fine. So, what is right hand side? Now multiply right hand side, expand the brackets. So what we'll get 1 plus x plus kx plus x square. This is right hand side. I am just expanding brackets, right? So if I combine these two, what I will get 1 plus k plus 1 times x plus some square term. Okay, now what I will do, I will neglect this square term and I will just I will just pick up this first two terms and I will just delete this. What will happen? Which quantity is smaller and which quantity is larger? right? I am removing some weight from this step, right? This is some amount or some weight, and I am removing some weight. And if I am
सर
removing,
पण निग्लेक्ट कसं करताय? Because it does
neglect
not
means I
build
am neglecting.
like
No, I am neglecting. Then I will get less quantity. Suppose you have 5 kg mangoes, and if you remove 1 kg mango, what amount you will get? The lesser amount.
yeah.
That is what I want to say. I am not saying equal. Is it
No,
clear?
no, no. But hey, Asa, it's not a small quantity. It's greater than -1, so it can be anything, na?
So
So
if
he might,
x is a real number, x square is
yeah,
always positive, always
yeah,
greater equal 0.
yeah,
Right? So if I am removing some positive amount from anything, whatever remaining is a lesser amount.
yeah,
So this amount is lesser than this.
yes.
That is what I want.
Okay, 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 okay,
Right?
okay,
That is what my ultimate aim.
okay, okay, okay.
So thus, what I get 1 plus x raised to k plus 1. I started with 1 plus x raised to k plus 1, and ultimately where I reach, it is greater equal 1 plus k plus 1 times x. Is it clear? And without any violating any rule, any law, I just use induction hypothesis, and I just remove some positive amount, so I can reach to the lesser amount, which is 1 plus k plus 1 times x, right? And that is what we wanted to get. This is we wanted to get, right? Hence, is it exactly what we wanted to find? Right? Okay, so hence the result is true for n is equal to k plus 1. So result is true for. Therefore, can I declare that key 1 plus x raised to n is greater equal 1 plus nx for every natural number?
सर ती लास्ट
Can I
टर्म जी तुम्ही x
declare?
स्क्वेअर लिहिली. हॅलो सर.
Yes.
सर ती लास्ट टर्म तुम्ही x स्क्वेअर लिहिली आहे ते kx स्क्वेअर आहे ना.
हा मग ती निग्लेक्ट केली ना.
Oh, sorry.
Okay.
Right. So here it is kx, but still it is positive, no problem, because k is a natural number. So, and I am see, kx square is a positive, that makes sense. Otherwise, if you neglect negative term, then quantity may not be smaller, it might be larger. But we are sure that if we remove this term, then our resulting quantity is smaller, because we are deleting or neglecting the positive quantity, right? So, okay, this is kx square, but still it is positive. If you neglect it, the resulting amount is smaller. That is what the main point we want to make, right? And hence this result is true for all natural numbers. Okay, so before going to next problem, let me note something. In mathematical statements, so in mathematical statement, most of the time we use some notations, right? So the notation that we use, for example, we use notation like these notations are called as quantifiers. So what are the quantifiers? The quantifiers are symbols that we use in mathematical statement. So for example, every for every n in n. So same thing I can write in short, for all n in n. So that you need to understand, because sometimes I am writing this kind of notation, so there should not be confusion. There exist I can say n in n. Then how do I write it? There exists n in n. So this is a notation or quantifier I use for existence. There exists. For example, uh, for example, for example, there is a natural number greater than greater than uh, 2020. So how will you write down this statement using quantifier? So the same statement I can write it as there exists n in n such that n is greater than 2020. This statement is true, right? Because uh, certainly I can produce a natural number which is greater than 2020, right? Or uh, one more example, let me tell you. For every real number, okay, I will every real number square of or square of every real number is positive. Is positive. So the same statement I want to write in short. So the same statement I will write it for every x in set
For
of,
all.
right, for every x in R, x square is positive, right? So okay, also let me tell you, this is what the notation for set of real numbers. So this is a notation we use for set of real numbers, and therefore for all x in R, x square is positive. So in that way, I am using somewhere this kind of notation, so you should understand this. Okay, fine. Now let us go to the next problem. Prove that prove that uh, for each n in n, for each n in n, n cube plus 3n is divisible by 3 is divisible by 3, right? So this is a statement which is true for all natural numbers, and we want to prove this, right? So okay, so what is the first step? What is my pn statement here? Pn, what is statement Pn? N cube plus 3n is divisible by 3 uh, for all n greater equal n in natural numbers, for all n natural numbers. So this is my statement. Okay, so to make our statements easy, what I should note here, note that uh, m divides n if, when we say that the number m divides number n, what is your for example 2 divides 6. When why 2 divides 6?
It
Because
it
6
satisfies its divisibility.
divisibility means 6 can be expressed as 2 times some integer, right? Right, because 6 is 2 times 3. What is k in this case? K is, therefore when we say that some number divides another number, that means that another number is multiple of, so the number 6 is multiple of 2, right? Or it is 2 is a factor, correct? So m divides n if there exists integer k, there exists integer k such that n is equal to m times k, right? So m divides n means there exists another integer k such that n is product of m and k, or m is a factor of n, then we say that m divides. So this is the standard way to divisors or when divides, so that you know. Okay, so and if you remember this way to understand this definition of divides, then our proof is becomes easy to express. So what is first step? First step, base step. So I will not write in detail because now you understand what are the details. You write down all the details. So if n is equal to 1, then what is our left hand side? If n is equal to 1, what is our left hand side? N cube plus 3n. So n cube plus 3n. But our n is a particular number 1. So what is it for n is equal to 1? So 1 cube plus 3 times 1. Right. Now, oh sorry, let me correct it. It is not 3 times n, it should be 2 times n. So it is 2 times n. It is 2 times n. 2 times n. 2 times n. So 2 times n, and what is it? 3. And which is divisible by 3. Right. So clearly this is divisible by 3, and hence result is true for n is equal to 1. Therefore Pn is true for n is equal to 1. No doubt, because it for n is equal to 1, the n cube plus 2n itself is 3, and which is divisible by 3 because it is 3 times 1. Okay, so step 2. So step 2. So what is step 2? Induction hypothesis. Right? Induction hypothesis. So what is induction hypothesis? Assume that that for n is equal to k, k cube plus 2k is divisible by 3. That means, that is, what is our assumption? For n is equal to k, k cube plus 2k is 3 times t for some integer t. So for some integer t. Okay. Have I told you the notation for integers?
Z, no, sir.
Z, right? I already told you. So, and therefore, we are assuming that k cube plus 2k is divisible by 3, means it is 3 times some integer. So it is a multiple of 3. That is what the meaning of divisible. So, what is our step 3? Inductive step. So, what we want, k plus 1 raised to 3 plus 2 times k plus 1 is divisible by by 3. This is our claim, right? This is our aim now, because we want to prove that result is true for n is equal to k plus 1. That means this thing is divisible by 3. Okay, now let us start with this. So consider. So let us start with this expression. So consider k plus 1 raised to 3 plus 2 times k plus 1. Start with this. Now expand this bracket, and all of you know how to expand. K cube plus 3k square plus 3k plus 1. So first bracket I have expanded in this way, and what is second bracket? 2k plus 1, 2. Am I right?
Yes, sir.
Yes.
Okay. Now somehow I want to use induction hypothesis. So and therefore certainly I should look at this, right? I should combine these two terms, k cube plus 2k. These two terms are important because that are there in induction hypothesis. Plus whatever remaining terms, this, and this. So if I combine these three terms, then what are these three terms? 3k square plus 3k, right? And 1 plus 2 is 3, right? Now, but first bracket, by induction hypothesis, we are already assuming that it is multiple of 3, right? So I can directly write down it as 3 times t plus, what is the second bracket? In second bracket, every term involves 3. So I can take 3 outside, and what remains in bracket? K square plus k plus 1. Okay, so I can say that now in these two terms 3 is common. I can say that it is t plus k square plus k plus 1. And what is this? Last expression is 3 times some s. And what is s? S is t plus k square plus k plus 1. Is it integer? Is s integer?
Yes.
Certainly, because it is addition of integers, so it is integer. And therefore, ultimately what we found, ki k plus 1 cube plus 2 times k plus 1 is a multiple of 3. That means it is 3 times some integer. So therefore, can I say that 3 is a factor of right hand side, therefore 3 is a factor of left hand side, and therefore 3 divides k plus 1 cube plus 2 times k plus 1, right? Hence, the result is true for n is equal to k plus 1, and therefore from k to k plus 1 we are able to prove. And what is our final conclusion? Thus our final conclusion is n cube plus 3n 2n is divisible by 3 for all n. That means for every natural number this result is true, right? And we need not to check for all natural numbers, so induction is sufficient. We can declare it is true for all natural numbers. Fine. So I will give you many examples for homework. I will upload on Google Class or our Teams also, but you can try to prove this. Prove that. Prove that 3 raised to n is greater than n square for prove that this is true for example, n is equal to 1, 3, and what is n is equal to 1 here? 1. So it is true. N is equal to 2, then it is 9, and here 4. So for all natural numbers, so you can prove it. So one more interesting example is for, which is non-trivial actually, for any real number what real number I should say here. Okay, for any real number t, cos of t plus I sine of t raised to n is equal to cos of nt plus I sine of nt, and this is true for all n, for all natural numbers. This is also true, and this is something you can apply some other properties of sine and cos, but here certainly you need to use induction. For any t doesn't matter, you fix any real number and then this comes out to be true for every natural number, right? So you try to prove this. This is not really difficult, correct? Now so sometimes our results not necessarily true for n is equal to 1, or it may not be true for n is equal to 2, right? But it is true for all natural numbers after certain n, right? So that induction, again, that is a version of principle of induction. The induction principle arbitrary base case. Arbitrary base case means what? In the previous problems, our initial stage was n is equal to 1, and then our results were true for all n greater equal 1. For right from 1, for every natural number onwards, the result was true. But sometimes it may happen that it is your result is not true for n is equal to 1, not true. For n is equal to 2, it's not true. But n is equal to 3, it is true. N is equal to 4, it is true. And for all remaining numbers, it may be true. So, therefore, initial stage, right? So, initial stage in this case cannot be 1. Initial stage should be 3, and then we should prove result for all natural numbers greater than or equal to 3. That would be the appropriate statement, right? So, and therefore our base case will be n is equal to 3. So what is the general version? Let subset of z. Now we are using this for integers, and n belongs to z. Suppose a is a subset of z and n is any integer. Now we are not confined with the natural numbers. Now we can say integers. A is a subset of integers, and choose any. Suppose n is some integer. Suppose n is this particular number n is a member of A, and for every k greater equal n, k is member of A, right? K is member of A implies k plus 1 is also member of A. So if n is a member of A and if you choose any member from A, then the next also is member of A. Right. So if you compare our original principle, induction principle, and this, what is the difference? That this capital N was 1 in that case in natural numbers, but this is a more general version. It is about integers, right? So then the set of, that means all the integers which are greater equal this particular number n, right? Remember that this n and this n are not same. Do you realize this? This is a particular number n and this is a set of natural numbers. So you should understand that these two are different things, this n and this n. Okay. So if you then what happens if you choose all integers greater equal n, then it is subset of A, right? So arbitrary case. So this is more general. That means this is true for integers. But as far as if you want to make this statement very simple, then I will make this as, suppose A subset of, so let A subset of natural numbers and n is some natural number. Suppose, so A is a subset of natural numbers and n is any natural number. Suppose n is a member of A and for every n, for every k greater equal n, k is in A implies k plus 1 is in A, right? Then the set of natural numbers which are greater than or equal to this particular is subset of A, right? So suppose n plus 1, look at this set, right? Suppose my capital N is 5, then 6, then 7, and so on. So this set satisfies these two properties. These two properties. This set satisfies because what is n in this case? N is 5, and if you add next one to this, 6 is there, 7 is there, all are, and therefore the set A contains this. This is what the meaning of this general version, right? And therefore, what are the steps? What are the main steps? So step 1, in this case, if you want to prove some result for in this general case, and your n is not 1, n is some bigger number, then what is the step 1? Prove for n is equal to n, right? What is step 2? Assume for k greater than n, and what is the step 3? Prove for k plus 1, right? Assume for n is equal to k which is greater than 1 or greater equal n, and then prove for n is equal to k plus 1. So ultimately what is our base step? N is equal to capital particular n, and then assume that it is true for every n greater equal this capital N, and prove for k plus 1. Though the method is same, only thing is what is our initial stage? Initial step is, or base step is capital N, right? So next time we'll see a problem on this, and then we'll go to the strong induction. All right, we'll try to see the strong induction. Okay, so any doubt?
So attendance.
Yeah, I have taken attendance. So I have downloaded attendance, and now it is 2 o'clock. So you have to join next class. Is it clear?
सर या
Yes.
क्लास कोड काय आहे?
Class code. I think I class code I mentioned it in the beginning. So let me check whether it is available here or not.
HRB 2LCK.
HRB to LCK, it is there. Okay, so any difficulty, any doubts?
No,
Sir,
sir.
I'm new student
Yeah.
and I don't get any login ID from the college.
So your admission is late
Confirm.
admission? No,
Ha.
but wait, late. So then you will get it later on, because the IDs are distributed to the students who got admission earlier. The
Ha.
later students will get later.
Okay, thank you.
Okay.
Excuse me, sir.
Yes.
Sir, you haven't added me in Teams yet.
Have you got ID,
Yes, sir.
and have you click a link to join team?
No, I had a link to join this class, right? So
No,
the
no.
link to join the team, I don't have that.
I have shared it on WhatsApp group, E Division WhatsApp group. Are you member of WhatsApp group?
Yes, sir.
In that WhatsApp group, there is a link, or I will share once again so that the new people can join the team. So through that team,
Okay.
you link, click on link, then I will receive your request, then I accept, and then you will be member of team.
Okay. Thank you, sir.
Okay.